Another week begins. That's crazy. Wow. Morning, Joey. Did you see that Tavares Jackson just died? It's insane. I'm missing Pleasant Kenobi for this. I'm sorry. These are your choices. Also, seeing the whole, like, there may be no concerts or, like, sporting events until fall 2021 thing that was just, like, put out last night. I really hope it's not a year and a half. That sounds terrifying. Yeah, Tavares Jackson died in a car crash last night. They just, like, sent me a text about that. I didn't see it this morning. That's insane. He was 36. And then, well, I don't know which news you were wait-whatting. But yeah, the other one, the World Health Organization guy came out and said that. So that's depressing news. Also, happy Monday. Here to deliver the happiest news, as always. Yeah, right. I mean, yeah, I think fall sports starting on time seems, fall sports with fans seems very unlikely. Whether they play, without them, maybe, but yeah, just from how things seem to be going, I think it's very unlikely that we're, like, playing with hundreds of thousands of people in stadiums in September. All right, so now that we're all pumped up and ready to start our week, let's do some algebra. NHL is still after it. I mean, so is the NBA, right? But, like, I just don't think, again, like, with fans, I don't think that's realistic. Without fans, like, yeah, sure, maybe they can televise it. I don't know. But it's not going to be for a while either way, I think. Okay, so let's just start with, like, where are we, right? So we've got 3 weeks left. Okay, so let's do a little recap here. So we've got 3 weeks, 3 week left, sure. 3 weeks left. We're not gonna have a third exam. I just don't think, like, rushing things, putting, like, another take home makes a lot of sense. So we're gonna have, like, 2 problem sets instead of so no third exam. There will be a final. Final will be take home. It'll be probably pretty similar to what you guys had for the second one. I just think that's really the only way this is super doable. Project, right? So rough draft is due next week. And I mean, that's most of the stuff. You got a problem set for this Friday. I tried to, there's a little bit more computation because of the symmetric groups. Some, like, putting things in terms of transpositions, some calculating orders, and I tried to give hints on the proof. So hopefully, it feels fairly doable. But again, I really encourage you guys to work together. Remember, you have that working together channel on the voice chat. You guys can just, like, send a text in our general chat and just be like, hey, anybody want to work tonight? And then, get together on that and talk about these things. I think that's super useful. And obviously you can use me as well. But yeah, I also recommend starting, not Thursday or Friday. I think that's about it. Any questions on stuff before we get started? Alrighty. Yeah, obviously feel free to ask whenever. Okay, so one thing I wanted to go back to, well, I guess two things from last time. One, no one called me out on this, but I straight up just like skipped one of the problems that we did last time. And then looking back through the dailies over the weekend, I think it's really important that we talk about it. It is similar to when we did 3Z, but nevertheless, I think it's worth talking about. So the index of 4z and z, right? So I made the mention when I assigned the daily that Lagrange's theorem doesn't apply here, right? And the reason for this is these are infinite order groups, right? This is infinite order. This is infinite order. We can't I mean, you should remember from calculus, right? You see infinity over infinity. You want to do like a L'Hopital's rule kind of thing when you're talking about limits, at least. And in general, like it just doesn't really make sense with division. So how do we do this? Well, this is where we appeal to the definition, right? So go back to the definition. So the index is not order of your group divided by the order of the subgroup. That is something that follows for finite groups from Lagrange's theorem, but it's not true in general, and it's not the definition. The definition of the index is the number of left or respectively right cosets. Again, they're always going to be the same, of H in G. So this is the general claim. And so for us, if we want this guy, we want to look for number of cosets, right? And this is where it is very similar to something we did before, right? So like your first coset, you just have like the identity, right? This is 4z itself. And this is also going to be equal to 4k plus 4z for any integer k, right? So like 4z is the set of all multiples of 4. So if you add some multiple of 4 to it, you're not changing that set, right? You're still a multiple of 4, and any multiple of 4 can be written like this. So all of these guys are equal, right? Because it's the number of distinct cosets, right? We want to be clear here. Like we're not double counting anything. We just count, the same set exactly one time. And then you would look at like 1 plus 4z. Well, this looks like what? So 1 plus some multiple of 4. So you got a bunch of stuff, and then you've got like negative 4 plus 1, 0 plus 1, 4 plus 1, and you keep going, right? These are all the things that are 1 mod 4. Okay, and all of these, right, if I choose 1, I choose negative 3, I choose 5, any of these are going to give you the same coset. And then you get 2 plus 4z and 3 plus 4z in the same way, and then you start repeating, right? So 4 plus 4z is 0, 5 plus 4z is 1 plus 4z, and so on. Right, so 4 plus 4z is back equal to 4z, 5 plus 4z equal to 1 plus 4z, and so on. So how many do we have? We have exactly 4 distinct ones, and so the index is going to be 4. Okay. And this is important because if you have infinite groups, this is the way you need to think about it. Okay, it's all about how many cosets there are. And again, this behaves a lot like Z4, right? And we'll see later how to make it rigorous that this set of cosets is truly a group and is isomorphic to the cyclic group Z4. Okay. So then last time I tried to get into like an element-specific argument for this 532, right? So if H is a subgroup of G and its index is 2. So again, this would apply for infinite groups. So think of the even integers inside the integers. This would be index 2. So Z mod 2Z, or the index of 2Z and Z is equal to 2, for example, just to get one that's infinite. Then our conclusion is that H is normal in G. And if we recall, right, H is normal in G if and only if AH equals HA for all A in G. Right, so your left cosets are always equal to your right cosets. So that's the definition of normal. Yeah, so I tried like an element-specific one, and that works, and it relies on 514, which is nice. We're using a previous result, but this also uses a previous result. So I gave you a suggestion over the weekend to think more in terms of the cosets partitioning your group, right? So the cosets of H partition the group G. So again, what does that mean? That means that the cosets union up to give you all of G, and if you have two distinct cosets, they do not intersect at all, right? So they share no elements. If they do share an element, then they're the same thing. And here we know we have only two cosets. Now, we always have one coset, which is H itself, right? The subgroup is always a coset because it's like E times H or H times E, however you want to look at it. So one of them is H, and then you want to think, well, our goal is to show it's normal, right? So our goal is to show that AH is equal to HA for any A and G. And so the way you want to do this, right, is, well, let's just look in general at some cosets. So if we want to partition, H is one of them. The other part is going to be some GH, right, where G is not in H specifically, right? Because if G is in H, then, well, GH would be equal to H. That's by 514. So this is by the partitioning and 514. Basically, for this to not be equal to H, then you need G to not be in H. And here, H intersect GH, again, this is by the definition of partition, is going to be the empty set. So this is for your left. But this is also true for the right. Right? So G is also equal to H union HG. And here, H intersect HG is equal to the empty set, where again, this G is, maybe the same one from above, where it's not in H. So the left cosets, the right cosets, they both partition things. So in general, take some A and G, right? We want to show that AH equals HA. Well, we have two cases, right? I mean, either A is in H or A is in GH. So if A is in H, well, then AH equals H and HA equals H. So we're good because it's just in H. If A is not in H, then by this partitioning, right, we know that A is in GH. And by 514, this is true if and only if GH equals AH. But, again, these guys don't intersect up here. And so, if GH is not equal to H and HG is not equal to H, but they union up to give you the same stuff, these guys have to be equal. right? And so down here, want that to go back to black. GH equals HG, so AH equals GH equals HG, and again, if A is not in H, A is also in HG, and so equals HA. So basically, we're still leveraging 514 a lot, but I think it's a lot quicker if you think about it in terms of partitions. Right, you're one of these two cosets, you're good. Does that make sense? And again, I mean, the other way you could think of it, right, is, never mind, that's fine, yeah. AH is one of two options. It's either GH or it's H, and it's either HG or it's H. And so they're either both H or both the one that's not H. And either way, you get the left is equal to the right. All right. So reading through 533 as I was looking this morning, there's a very long way to do this, and then there's recognizing that this comes right after 532, and thus a very short way to do this. So here, right, we have S, which is a subgroup of R squared, R squared and S squared, this guy, and this is a subgroup of D4, right? And you should probably check and see what exactly is in here, right? Because it doesn't seem like, oh, well, maybe S is not in here. But it is, right? So we've got E, we've got R squared. If you do SR squared times R squared, you get SR to the fourth. But R to the fourth is E, so you get S, and then you get SR squared. And if you try any combination of these, you'll see that you stay in there, right? Because in D4, R squared S is equal to SR squared. So this is really a group of order 4. So what we want is that these are actually both normal in the one above them, but S is not normal in D4. Essentially showing that like normality is not, well, it's definitely not going to be an equivalence relation because of symmetry as well, but it's not transitive is what we're showing here. So why is this true? Well, think about the orders here, right? So order of S, subgroup generated by S is 2. We just check the elements of this guy. It had order 4, and the order of D4 is 8. Well, now we can calculate these indices, right? So the index of the subgroup generated by S in the subgroup generated by R squared and SR squared. Well, this is going to be exactly 4 over 2, which is 2. And the index of the subgroup generated by R squared and SR squared in D4 is 8 over 4, which is also 2. So both normal. That's just by the previous problem. Right, so that's your fast way to do it. I mean, you could actually calculate out all the cosets, but that seems like a lot, and I highly recommend not doing that. But for the last one, right, to show that the subgroup generated by S is not normal, well, you don't have to show all of them are equal. Just one counterexample suffices. So we've seen this before early in the chapter. Which one doesn't work here? So why is the subgroup generated by S not normal in D4? Do you have an example of a left coset that's not equal to a right coset? Yeah, that would work. Yeah, this one works. You also could just do R. Might be a little easier to check in some ways, right? Because this one has RS, this one has R cubed S, while the other element is S, or sorry, while the other element is R. This one is similar, right? So here you would get what? R cubed versus R. Right, R cubed is in here, R is in here, but the other one is not. Yeah, and so once you have one, you're good. And so it's not normal. And this is also going to be a useful thing to know later when we talk about normalizers, because the subgroup S generated by S comes up again there. Okay. Yeah, and so here, right, like this guy is equal to RS and R is equal to R cubed S and R. And I guess I can actually just go ahead through this. So what's in here? So you have S times SR, which is R, and then you have SR, and then over here you have SR, and then SRS is S times SR cubed, so you get R cubed. Okay, so that shows that they're not equal explicitly. Okay, so those are just some examples where you're just checking normality, looking at left cosets, right cosets, thinking about them. And I really do want you to try to think more about the theorem. So like really that use of 532, it's not just applicable in this problem, it's going to be applicable in one of the ones on the normalizer problems as well. And in general, like with these things, you can imagine how I could easily ask about groups that are bigger than order 8. In which case, you know, if you try to kind of figure things out by exhaustion, you're going to think that's not a very efficient route, right? And if I give you a bigger group, that's going to be a real problem. And so you want to think, is there an easy way to do this first? Do I have tools that I've developed here recently that can be useful to me? And see if those apply first. And then if they don't apply, then, okay, maybe you do have to do kind of a more rudimentary approach, you know, and that's okay. You know, if you have to, you have to. But always look for the shortcut first. Okay. All right. So the next thing we want to get at is another definition of normality, and this is the one I think you usually see, or what I usually employ. So recall, right? Again, I said this earlier. H is normal in G if and only if for all A and G, AH is equal to HA. And then our goal in this problem is to show that we could give another definition that H is normal in G if and only if G inverse is contained in H. So let's think about this for a second, right? So one, we have a name for this, right? This is conjugating the subgroup by the element G, right? Conjugation is something we talked about a little bit. So what may seem weird here is that I have a subset, right? Because if you just look immediately at this definition, you're just like, okay, H is normal in G, so I've got this, and then all I do here is like right multiply by G inverse on each side, and I'll get G inverse equals H. And I'm good. And that's true. This is actually a weaker statement, right? Which is nice because showing equality is harder than showing subset one way, right? So this is saying you only have to check this, and then you get equality for free. And so it's kind of nice that we can make this claim that something weaker will actually do the trick. But it seems maybe not intuitive to see that subset there. So our goal is really to show that that is enough, right? So one direction is very easy because of this, right? What we just showed is this direction, right? So if H is normal in G, then GH equals, so again, this is for all G and G, for all G and G, so GH, G inverse equals H for all G and G. And if they're equal, Well, clearly this is going to be a subset, right? Because they're both subsets of each other. And so that way is very simple. The other way requires a little more work, okay? So why is just containment enough, right? So suppose we have this containment. We want the left coset to be equal to the right coset, right? Okay, well, again, we can just kind of like right multiply by g and at least get one of these, right? So right multiply by g to get gh is contained in hg. Well, that's good. But then we still need the other way, right? We still need hg is contained in gh. So remember, this is actually true for all g in g, right? So we have the freedom to choose. So maybe I should say, let me just change this ever so slightly here, just to make it not too confusing notationally. So we want AH equals HA for all A in G. So let's start with, I probably could have done it there, but just to not confuse my notation at all. So we know AH, A inverse is contained in H. So right multiplying by A to get AH is contained in HA. Okay, so now to get HA is contained in AH, again, we get to choose the G, right? So here I chose G to be A because that gave me that side. What G do I want here? Well, if I see what I did here, right, like I ended up right multiplying on each side to get AH is contained in HA. So if I have, right, I want A to end up on the right. And so how am I going to get an A on the right? Well, that would be by right multiplying by A, right? But then I wouldn't get HA over here. So I have to change my G, and what I want to change it to is A inverse. Right? So if I have the inverse, then I'm going to basically get, the opposite way because of how I just did things. So then we know, by assumption, that A inverse H, A inverse inverse is contained in H. But I mean, what is A inverse inverse, right? It's A. So we have A inverse HA is contained in H. So, we left multiplied above, we right multiplied above. Well, now we're going to cancel out the A inverse by left multiplying. So, left multiply to get HA is contained in AH. Okay? And so that's the trick. The key is that you know it for any G, and so you have the choice. And so that's the trick, is that it's also true for its inverse, and so you have to use both of them to get the result. And so that gives you normality. Does that make sense? Any questions there? So one reason why this is useful is it like reduces work a little bit, right? So just like a little example real fast. Not that this was an especially hard one anyway, but, you know, again, showing that like S is not normal in D4, right? So upstairs we had to look at two different cosets, right? And I was just like, all right, RS is not equal to SR, but like I actually calculated both of these things, right? And I get these four elements combined. It's just like a little bit more work than instead saying, okay, I'm going to check one thing. What is RS R inverse? Well, that's RS R cubed, and SR cubed is RS. So this is R squared S, and this guy is not in S, right? So this immediately tells us that R subgroup generated by S, R inverse, is not contained in the subgroup generated by S. So by just checking one element, I was able to say that this is not normal instead of like finding the whole cosets and seeing whether they were, you know, equal or not. Okay, so it makes things a little bit faster there. Okay. Well, seeing no questions, wanted to next focus on the normalizer. So the normalizer should have looked not too unfamiliar. Right, we've seen things somewhat like it with another izer. We had the centralizer, right? This is subgroup of things that like all commuted with one element. Here, and on our test, right, we saw the centralizer of a subgroup is also a subgroup, right? And this was the set of x and g such that xh equals hx for all h and h. Right, the things that commute with every element of H. And here, our normalizer is going to be defined as the things that normalize H, or basically the G and G. I don't know why I used X there. Whatever, it's fine. G and G such that GH, G inverse is equal to H. So again, you could say subset, and that would imply that it's going to be equal. So, you know, it doesn't really matter. But this is just the definition I put in the book, so I'll just keep consistent with that. But yeah, basically these are the things that make H normal, right? And so essentially, if it works for all G, so if G is equal to the normalizer, well, what does that mean? That means every single element in your group normalizes H, conjugates H to H. Well, that's exactly by our previous theorem, right? Our alternate definition of normality, going to give you the fact that H is normal in G. Right, so somewhat like the center or centralizer tells you like how close you are to being abelian. Right, so here it would say like, you know, if the centralizer in G of H is all G in G, then that means that everything commutes. H is, well, I mean, H itself would be abelian, and yeah, it's a nice property, right? And then like the center of the group being equal to the whole group, that told you that your group was abelian. These are nice things. So here again, like this top case where the normalizer is your whole group tells you that your subgroup is normal. And then if you are, you know, far away from that, so think in terms of your subgroup lattice. So if you have like a lattice here, and you've got like G, K, H, you know, maybe there's more stuff in between, right? So if this is your normalizer, then this means H is normal in G. If this guy is your normalizer, then this means that nothing outside of H conjugates H to H. right? So this is like as far away from being normal as you can be. So far from normal. And then this is something in between, right? So you're maybe a little bit closer, and basically the higher up the ladder that your normalizer goes, the closer you are to being normal in your group G. So that's the idea here, right? And it's similar with the center. Like the center, the closer it is to the whole group, the closer your group is to being abelian, right? So it's a similar notion in that sense. And why did I stop here, right? Like, why didn't I stop at E, right? The trivial group is maybe below here. Maybe H is not the trivial group, and so I've got something lower. Well, note that the normalizer always contains H. Why is this true? Well, think about it. What's the definition? Since for any H in H, H inverse, well, we have closure, right? So this is always going to be contained in H. Right, we're just multiplying elements of H by elements of H, so we're going to stay in H. So this is always true. And so the normalizer has to at least be as big as H, right? It must contain H. Shouldn't say big because it has nothing to do with cardinality. It must at least contain H. Okay. So, why is this useful? Well, I think this next theorem is helpful. So the normalizer is going to be, so remember back when we talked about like intersection, right? The intersection was the largest subgroup contained in both H and K, right? So you had something like H, you had K, and then you have this guy. And this was like the largest subgroup such that it's below both of them, right? And contained in both of them. If you have something else, say L, that also had lines going up, then there had to be a line here. Well, this is the same kind of notion, right? So if you have a subgroup that H is normal in, then this is going to contain that. So, I guess first we do 537. Sorry, show it's actually a subgroup first, and then we'll talk about why this is the largest one in which H is normal. And again, if you have questions, feel free to throw them out. But yeah, not seeing anything. Okay, so seemed like most people had this one down when I was reading through it this morning. So I was pretty pleased with this. So if G is a group, then the normalizer is a subgroup. Okay. Well, as you guys were doing, subgroup test, right? So first we want to show it's non-empty. Well, the thing we usually check non-emptiness with is E, right? So if we have E, H, E inverse, well, this is just H, right? I mean, E inverse is E, and it's not changing anything anyway. So this exactly gets you to set H back. So E is definitely in the normalizer. Okay, good. So it's not empty. We're happy. Closure. Okay, so if we want closure, right, you start with a couple of elements in there. This is where I did want to make one comment in terms of notation. So I was seeing a lot of like let G and H be in the normalizer. That's dangerous because if you're using little h, most people are going to assume that's in H because they're both H. And you want to be careful here because we're only assuming it's in the normalizer, not in H itself. So, you know, I would prefer like a G1 and G2 or an X and Y in there just in terms of notation, even though if you say little h is in here, then like explicitly, yeah, you are correct. It just feels weird. So what does it mean to be in the normalizer, right? That's the first question because we want to show x, y, the product is in here. Well, this exactly means that xh, x inverse is h, and yh, y inverse is h. So let's check the product, right? Like what happens when we conjugate. So therefore, when we look at this guy, well, we know socks and shoes. So we have something like this. But then what you notice, right, is, well, of course we have associativity. You can group these guys, and then you can group these guys and kind of collapse it down to H in 2 steps, right? So this is X, Y, H, Y inverse, X inverse, but this is in the centralizer, so this is equal to H in the middle. And that's also in the centralizer, so this is equal to H as well. Right, so we're just applying the definition there. And then inverse is similarly not too bad, right? So let X be in the normalizer. So XH, X inverse equals H. What do we want to show? We want to show that X inverse H, X inverse, or just X, is equal to H. So you just left multiply there, and then you right multiply. And again, this is, if you want to be real pedantic, X inverse, and so it's exactly of the right form, right? So X inverse is in the normalizer. And so we've got a subgroup. Okay, so we've already shown that H is always contained in the normalizer, right? And so we do know that our lattice has something like this, where these could be equal, right? Could be equal. The question is, why is it always normal, and then why is the normalizer the largest such subgroup? Okay, so that's addressed in this next theorem, and this is the really important one. This is how you usually think of the normalizer. It's the biggest subgroup in which H is normal. Okay, and so that's why we can think of it as some measurement of being normal in G, because the bigger that the normalizer of H is, right, the closer it is to the whole group itself, the closer H is to being normal in G. So here my claim is that H is normal in the normalizer, and this is the largest subgroup such that H is normal in it. It's poorly worded. Largest subgroup of G in which H is normal, whatever. We all have regrets. All right, it's fine. So first let's show it's normal. So what do we need to show? Well, it suffices, right, to show that for any H in H, right, so H is normal in G, or sorry, normal in G of H, if and only if H, geez, G inverse is contained in H for any G, not in G this time, but in the normalizer, right? So, well, think about the definition of the normalizer. And then this is not hard at all, right? So, G is in the normalizer if and only if G inverse equals H. Therefore, G inverse is contained in H. So, and this is true for any, right? So, thus, H is normal. Like, this is basically by definition of the normalizer, right? I mean, that it follows because this is exactly the thing that we want, right? And we define it that way. So, these are the things that already make this true. All right, so that one follows really quickly. So the real content of this problem is this part, right? It's the largest such thing. So, right, if we've got h, we know this. So what we want, if it's going to be the largest, then if h is normal in some subgroup k of G, then K must be contained in the normalizer. This is what it would mean by largest, right? So if some other thing satisfies the same property, if H is normal in it, then it must have been smaller than the normalizer, right? Could have been no bigger. So how do we show this? Well, we've turned it into an if-then statement. I mean, let's check it out, right? So like, what does it mean for H to be normal in K? So if H is normal in K, then for any x in K, xh, x inverse is contained in H, and therefore, again, this implies equal to H. That was by our 535. Right? We showed that subset is enough, but this means that it's actually equal to. Well, what does this mean? This means exactly that x is in the normalizer, right? This is just the definition of being in the normalizer. So, thus x is in the normalizer. So what have we shown? If I take an element of K, then it must have been in the normalizer, right? So thus, K is a subgroup of the normalizer. And so the normalizer must have been the largest such thing. Okay. Questions on that before we do a couple of examples with actually computing some normalizers? This is more of me proving stuff today. So please ask questions if you have them. Alrighty. Okay. So for these, again, there's like a quick way and a long way. So proving that it's a normalizer is the same as a centralizer. No. Not necessarily. Oh, okay. Are you saying that because, right, so GH, G inverse is equal to H implies that GH equals HG. So you're kind of saying like this looks a lot like the centralizer, right? That these commute with each other. It's not exactly true because you can have GX equal to YG, where X and Y are in H, but X is not equal to Y. So all this says that the sets are the same, not that they actually, the elements commute. So, right, like GX, if I switch the order and then do an element of H times G, it may be a different element of H. Whereas if you were in the centralizer, it would be the same element of H. So that's the difference. That's a really good question. Yeah. So it's subtle there. So not the same as centralizer. Yeah. Okay. And we'll see if we come up with an example here. So the first one is we wanted to look at the normalizer of V4 in D4. So again, there's like an easy way to do this and a hard way to do this. You can look element by element, but think about the orders again, right? So like V4 has order 4. D4 has order 8. So V4 is normal in D4 by 532, right? This is an index 2 subgroup. And if I know it's normal, right, again, we want the normalizer is the largest subgroup of G, or in this case D4, such that V4 is normal in it. Well, if it's normal in the whole thing, you can't get any bigger than the whole thing, right? So this tells you immediately that the normalizer is the whole group. Right, so that's the fast way. And then the long way would be to actually just like compute out the elements, see what happens, see what normalizes what, and actually compute the normalizer like element by element. But again, use the tools that you have. And then this next one, again, I think there's a fast way and a not so fast way. So here we have seen, so we talked about S in D4, but it's true in D3 as well that this is not normal. Right, so again, just because RS is not equal to SR, that's kind of the crux there. So if the group is normal in another group, then the normalizer would be that other group. Not necessarily. It has to be the biggest one. Right, because like a group is normal in itself, but that doesn't mean its normalizer is itself. So like it's very much the largest that's the key word there. Yeah, good question. Right, so here, again, thinking largest in the fact that it's a subgroup, right? So in D3 of this is a subgroup of D3 and contains the subgroup generated by S. Well, what does our D3 lattice look like? You've got several reflections, and then your rotation, and then all of these obviously are contain the trivial group. So if I look here, and I know my normalizer at least is at least as big as this, but is not the whole thing, well, if I go up here, it's not this, and it has to be at least this. There's nothing in between. So like this must be the normalizer. Since it's not D3, but contains the subgroup generated by S. Right? You only have one option. And so this is one of the really nice things about small groups is you can actually just like look at the lattice and just rule everything out immediately the second you know that it's not normal in the whole group. Okay. So this is pretty much the you'll see a couple problems on like a homework about this, but in terms of class time and the dailies, we're going to be moving on to products and quotients after this. So if you do have questions, like please go ahead and ask them. I mean, we're out of time now, but I'm happy to answer questions. And then if you don't have anything, I can cut stream and go to Discord. But yeah, feel free to ask questions about these. Because we will definitely be switching gears quite a bit on Wednesday. Yeah, so I mean, maybe one more thing. What Mark just threw up in Discord is an interesting centralizer problem. It would take some work because we haven't dealt that much with centralizers of, well, subgroups in general. We just kind of prove that, and especially we haven't dealt with the alternating group too much yet. That's a lot of what this problem set is about. But yeah, centralizer versus normalizer can be very, very strange. So again, A4 is normal in S4. Why is this true? Well, this is n factorial over 2. Here, I mean, this is just 12. This is 24. And so the index is 2. Right, so this is normal. Thus, the normalizer in S4 of A4 is equal to S4, right? But the centralizer in S4 of A4 is actually the trivial group. And I'm not going to say this should not be surprising, but at the same time it shouldn't be completely unintuitive, because we know that for most permutations, right, like order very much matters. And in this case, like order really matters. Basically, the only one that commutes with all the things in A4 is the identity itself. And so that's kind of a cool thing to check out, and gets more into Clark's question there as to why these are not the same thing, right? So, I mean, you do have that GA4 is equal to A4G, right, for any G in S4, but if I take GX, it's not going to be equal to XG for any G not equal to E. Sorry, there would be something that it doesn't commute with. Geez, that's rough. Not for some X in A4 if G is not equal to E. There'd be something that won't commute with it inside A4. Okay, so yeah, that's a cool example. And so they can be very, very far apart from one another, which is kind of cool because, yeah, again, they look similar in terms of the equations that you're getting, but how they actually behave is really different. Alrighty, well, I will be around for a bit now, and then, this afternoon, if you have questions on stuff. Again, I recommend starting on that problem set a little bit early. That way you can have time to ask me questions, and I very much encourage working together. All right, have a good day.